thanks for watching, and today I want to show you an example of when fxy is not fyx. Because I'm sure you've always been told that mixed second partial derivatives are equal, but I want to show you that you have to be very careful about your assumptions. Because technically, this is not true for every function. The requirement is you need to have that both of those things are also continuous. So let me give you this pathological example, and I will show you later why we would even think of choosing that. So consider the following function. F of xy is defined as follows. So it's xy, y squared minus x squared minus y squared minus y squared over x squared plus y squared if xy is not equal 0, and then 0 otherwise. So at 0, 0, it's 0. And my goal is I want to show that at the point 0, 0, the mixed partial derivatives are not equal. It's not equal f of yx 0, 0. By the way, this is called Clairaut's theorem or Schwarz's theorem. And the cool thing about Clairaut is he had 19 siblings, which is, I think, pretty crazy. And also he published his first math paper when he was 12, which I think is even crazier, but good for him. Alright, so how do we do this? We will evaluate those very carefully. So first of all, let's calculate the x derivative at 0, 0. So fx at 0, 0. Again, what's the definition? You start with the point 0, 0, and you add something small to this 0. So f of h comma 0 minus f of 0 comma 0 over h, and you take the limit. Alright, but this is not too bad to calculate because by definition, f of 0, 0 is just 0. And also notice, if you let y be 0, then f of x 0, that's just x times 0 times some other junk over some other junk. So, in particular, on the x-axis, f is just identically equal 0. So, no matter what h we pick, this is always 0. So for every h, you're just taking the limit as h goes to 0 of the 0 function. And that one's just 0. And you can do something similar with fy at 0, 0. Well, that is limit as h goes to 0 of f of 0h minus f of 0, 0 over h. And again, you can show that this is always 0, this is always 0, so this is 0. So interestingly, the first derivatives, they exist at 0, and there's no issue here. The issue is really about the second derivatives, so let's calculate those now. So let's first do f of xy, 0, 0. And again, what this is, strictly speaking, you take f of x and take the y derivative of that. So, what this means, again, maybe let me emphasize. You take the function fx and increase y a little bit. So what this is, it's the limit as h goes to 0 of fx 0h minus fx 0, 0 over h. Now, the nice thing is, we already calculated fx 0, 0. We know that this is always 0. So all we need to calculate is fx at the point 0h. So let's calculate first of all the xth derivative of f. So, and for this, I believe now, because we may assume h is non-zero because we're taking the limit as h approaches 0, which means our point is not 0, 0, so we can legitimately use this formula here. So all that we need to do is differentiate that with respect to x. So take f of xy to be, if you expand this out, you get x cubed y minus xy cubed over x squared plus y squared. And now take that and differentiate that with respect to x. So fx xy. For this now, you use the quotient rule or the quotient loop, and you differentiate the numerator. So 3x squared y minus y cubed. So numerator prime times denominator minus numerator minus xy cubed times denominator prime, which is 2x, and then divided by denominator squared, so x squared plus y squared squared. And let's expand this out. Yeah, let's do that and then plug in our points. So then we get 3x to the 4th y, and then plus 3x squared y cubed minus x squared y cubed minus y to the 5th, and then minus 2x to the 4th y, and then plus 2x squared y cubed. Again, divided by x squared plus y squared squared. Okay, I know this looks like a horrible expression, but I think it simplifies. Let's see what happens. So what this becomes, we get, let's see, so x to the 4th y, yeah, we have one of this and then one of this, so basically 1 times x to the 4th y. And then this one, so 3 plus 2, 5, minus 1, so 5 minus 1, 4, okay, plus 4 x squared y cubed. And lastly, minus y to the 5th over x squared plus y squared squared. Okay, very good. So that is fx xy. And now, let me just double check. Yes, that looks correct. Now, all we need to do, so that is fx xy. Now let's do fx and 0h. So all that it means plug in x equals 0. So 0 to the 4th y h plus 4, 0 squared, h cubed, minus h to the 5th, over 0 squared plus h squared squared. And then what you're left with is, so this is just 0, and then minus h to the 5th, over h to the 4th, and that's minus h. All right, very good. So what does that mean? We can now plug this into this limit. Limit h goes to 0 of minus h minus 0 over h, and that's just minus 1. So interestingly, fxy at 0, 0 is minus 1, and let's do the other way, or if you want, you can just scroll fast forward if you like. Let's now do f of yx at 0, 0. So f of yx at 0, 0. So again, that's f of y x at 0, 0, and that is the limit as h goes to 0 of f of y, h comma 0, minus f of y, 0, 0, over h. This is, again, we calculated that to be 0. And now all we need to do is calculate fy. So this is our formula for f. All right. Fy is xy. Again, let's quotient rule this again. So x squared is x cubed minus 3xy squared times x squared plus y squared. And then minus x cubed y minus xy cubed. And then times 2y. And then divided by x squared plus y squared. Squared. And again, let's expand this out. So we get x to the 5th. And then plus, I think, x cubed y squared. Minus 3x cubed y squared, and then minus 3xy to the 4th, and then minus 2x cubed y squared, plus 2xy to the 4th, over x squared plus y squared, square. Check. Yes, looks correct. Okay, so simplify this a bit. So this is, we still have x to the 5th. Now let's see, x cubed y squared. So we have one of this here, one of this here, and then one of this here. So 1 minus 3 minus 2, that's minus 4. X cubed y squared, and then minus 1 plus 2, so minus xy to the 4th over x squared plus y squared squared. So this is fy xy, and therefore fy of h0, that is h to the 5th minus 4h cubed 0 squared minus h 0 to the 4th over h squared plus 0 squared squared, and this simplifies to h to the 5th over h to the 4th, and that is h. So in other words, this limit becomes limit as h goes to 0 of h over h, and that's 1. Da-da-dum! So yes, unfortunately, this function is pathological enough because we have shown that f of xy at 0, 0 is minus 1, but f of yx is 1. So f of xy of 0, 0 is 1, but f of yx at 0, 0 it's minus 1. So in particular, at that point, f of xy is not equal to f of yx. So in general, f of xy is not equal to f of yx. And I think what is happening is that at those points, the functions, they're not continuous. So I believe, because if you plug in h0, you don't get the same thing as plugging in 0h. Something like that. And in fact, if you do the proof, so the idea is, the problem is with interchange of limits. So in all those cases, what you get, if you actually try to do the proof, you get something like limit h goes to 0, limit k goes to 0, of something f of h comma k, minus f of h comma 0, minus f of 0 comma k, plus f of 0 comma 0, something like that, over h squared. So that is So writing either f of xy or f of yx as a limit, and the issue is precisely that you cannot always interchange the limits, because if you could, then f of xy at 0, 0 would be f of yx at 0, 0. So, in other words, you have to be a bit careful in analysis. That's why the main feature of analysis is teaching you to be scared of, especially interchanging limits. And last but not least, what I wanted to say is, why would you even come up with this function? Well, if you have noticed, we have x squared and y squared, so that should remind you of polar coordinates. And in fact, this function is very easy in polar coordinates. So I would like to remind you f of x, y, it's nothing else than xy times x squared minus y squared over x squared plus y squared. Now, if you just let polar coordinates happen, then x is r cosine theta, y is r sine theta, and then x squared minus y squared just becomes r squared cosine squared of theta minus sine squared of theta, and x squared plus y squared is just r squared. So let me just check. Yeah, okay, good. Then what you get, the r squares cancel out, and what you're left with, it's simply, so r squared cosine theta sine theta, which you can write as sine of 2 theta over 2, and cosine squared minus sine squared becomes cosine of 2 theta. And in fact, you can do more than that. This you can write as sine of 4 theta over 2. So r squared over 2 sine of 4 theta over 2. So it becomes r squared sine of 4 theta over 4. So in fact, if you think about this, I know it doesn't look that pathological here, but this function, what this does, it's kind of on every circle, it just oscillates 4 times. So it's a function that's kind of crazy. It just oscillates 4 times, no matter what small of a circle we have. And generally, for nice functions, they should not, the smaller the circle it is, it should not oscillate that crazily, like x squared plus y squared. That's a perfectly smooth function near 0, 0, but there's no oscillation happening around that point. Whereas this function, it just oscillates a lot around the point, no matter what small of a circle we have. So that is kind of the intuitive explanation of why this function is actually pathological. And this one not too bad to write down, but it leads to this horrible expression here. So there is this connection. Alright, I hope you like this little Clairaut extravaganza. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.